So I'm going to talk a little bit about a different sort of influence that deep learning has had in a different area, so in neuroscience, actually. And it's a great pleasure to talk among so many great friends and colleagues and great entrepreneurs and engineers and scientists. And recently I've been working on a company trying to tackle a very high and important problem with a purpose. This company is called Bay Labs. One more in the previous career, I was in neuroscience at MIT, so working in essentially this intersection between deep learning and neuroscience. And in some ways, we haven't really heard the whole story of deep learning and its roots and its origins, but there's a lot of overlap and synergy between these areas. And this work I'm talking about here is essentially our work to try to compare some of these latest deep neural networks to the actual brain, so the actual neurons inside the primate brain. This is a great, like a collaborative work between a lot of different elements here. And working in Jim DiCarlo's lab at MIT. And in Jim DiCarlo's lab, we record from neurons in the awake macaque monkey. And what that allows us to do is to help understand neural computation. It helps us to prevent and to cure disease. It also helps us to understand essentially visual object recognition at large. And so in creating this work here, there's a lot of people that have come together here. And I want to point out the people on the experimental side that have really gone through the laborious process of collecting these neural data sets. And so Najib, Majaj, and Ha Hong were really influential in getting this type of data set. And in fact, this is a neural data set that's small in comparison to ImageNet, but it's actually about an order of magnitude larger than any other neural data set of this type. Also on the computational side, Dan Yammans and Nicola Pinto really helped this analysis and kind of laid some of the foundations of this work. So the punchline of my talk is the title. So to give it away right here, it is that these deep neural networks actually rival the representation of primate IT cortex for core visual object recognition. All right, so that's kind of a mouthful there. There's some jargon in there, some specific terms to try to essentially delineate what this real finding is. And through the course of the talk, I'll kind of unpack each one of these terms for you to help you understand what the real result really is. But at large, the kind of bottom line is that the thing that's been incredibly exciting here is that for the first time, what we're seeing is that these artificial models actually begin to rival and possibly even surpass in some ways the neurons that we measure in the primate brain when it comes to object recognition. So this has been a really surprising result to us. So let's first start off with IT cortex. So what is that? So okay, cortex is the large part of the brain. This folded cortex here is a schematic of the primate cortex, the macaque primate. And so in neuroscience, especially in visual neuroscience, behavioral neuroscience as large as well, we use the macaque brain as a model, or essentially as a proxy for the human brain. And because it shares many properties, many visual areas, especially with the primate brain. And in this little schematic here, we have the eye, where visual information comes in, which then passes through the LGN and the thalamus, and then in through the visual hierarchy, through V1, visual area, primary visual cortex, V2, V4, and then through a series of areas or a region called inferior temporal cortex, and that's what IT is. And so the areas of the brain that we're pointing out here are called the ventral stream, and that ventral stream has been long known to subserve or to usually be engaged with object recognition. So you know sort of that through these different visual areas, there's some sort of transformations that are happening, some computations that allow us to recognize faces in the world, allow us to recognize objects under all kinds of different variations, and achieve these abilities that have been, at least so far, been quite unique to biological systems. And then as scientists, we begin to study this very complicated problem of all of visual behavior, all of visual recognition, everything else that's related to vision as well. You try to, kind of consolidate the problem and be a little bit reductionist in some ways. And what we're really trying to look at in this type of work is what we call a rapid object recognition or visual object recognition in a glance. So what we mean is like to flash an image and be able to, for example, make a discrimination on that image, is it a dog or is it a cat, in a very brief reaction time. So we know that humans can give accurate reaction times in the 150 millisecond range and certainly have robust behavior within a fraction of a second. So well beyond under 500 milliseconds. In the macaque brain, it's even less than that. Robust behavior of making correct discriminations on visual objects in the 250 millisecond regime. So how does this happen so quickly is another kind of aspect of this, this sort of miraculous biological behavior. And if you look at the way the information propagates through this ventral stream, probably the numbers are a little bit too small here, but you see if you flash an image, you see an incident spikes. So the neurons are spiking, and you see the first spikes at specific time periods after the incidence of the image. So when you get to IT cortex, you start in the macaque brain, you start to see these first spikes between 70, 100 milliseconds after when you show the image. And this very closely corresponds to, if you count essentially the reaction time of actually having to press a lever or press a button, for example, corresponds to about the behavioral limit of when we see object recognition happen. So we think that essentially this IT cortex is like the place where object recognition is happening in the brain. And what we do in the lab is essentially we put electrodes into those areas, and we actually measure the neurons in those areas and show images. So what kinds of images are we showing? Well, here's a little demonstration of how we test people in this specific task, which we call core object recognition. So what you're seeing here is an image flashing in the center of a screen. And in this case, it's a 7-way discrimination that we're asking people to do. And there are different classes of objects, faces, tables, airplanes, fruit, cars. So kind of just some big object categories there. And the images are of a certain sort. So they're not the same types of internet-like images that you see from ImageNet. They are of a specific type of sort where we have constructed them with very tight control over these images. So because of the way we construct them, they have a rather artificial appearance to them, admittedly. But it allows us to have very tight control over the parameters that make object recognition hard. And this object recognition is hard because, in this case, of things due to different faces, different types of fruit, different exemplars within the category. It's also hard because of the variation due to where that object lies in the retina. It's also hard because of the different sizes and scales that appear in the scene. It's hard also because of the backgrounds that we see and the poses of the objects as well. So with all these different combinations, we know this is a very hard computational problem. And it is then again miraculous sort of that the brain is able to solve it. So in this light, what we are calling core object recognition has a very series of reasons why we're studying this. It has very nice robust behavior I talked about. We know the neurons are spiking in a way that seems to be corresponding to the behavior, and we know from much work that these neurons have responses that seem to be selective at high-level properties of objects. Until recently we know that this task was very hard for algorithms, and I'll eventually show you the progress that's been made over the last few years, in fact. And we know that's also practical for many different tasks out there for object recognition. And here's just a little blow-up of some of those images, and again, like why this is hard. So, you know, if you reduce or you remove these variations, if you remove the position effects, the scale effects, backgrounds, and whatnot, then actually this problem is relatively simple, and we've had techniques for almost decades that can solve it. But it's the introduction of all these variations, all these variabilities that make this problem hard. And so that's really the key thing that we're trying to test here with these types of images and push these models and the brain to its limit. All right, so the next thing we wanted to unpack is this idea of a representation. This is a little bit different than just pure performance. Instead of just saying how accurate is a classifier, what do I mean by representation? So representation is essentially an indication of something else, maybe something out there in the world or a concept. It could be a theoretical concept. It could be something as concrete as, you know, the people sitting here in this room. And to take an example from David Marr, we can think about representing numbers. So when we want to represent a number, we have actually many choices to how to represent a number. And we have, for example, you know, Arabic numerals, binary numbers, Roman numerals. And I want to point out, though, that there's no best way to do this, right? The best way to do this often depends on your use case or how you're intended to use the representation itself. So we know that, you know, Arabic numerals have been great in terms of education and being able to, us humans, to manipulate numbers, be able to do arithmetic, for example, where Roman numerals are it's really difficult for us to do arithmetic with Roman numerals, where binary numbers are great for computers when you want to do digital signal processing, for example. But then we are also faced with these same sort of representational problems when we get to images. So it's how should we represent images is a big issue. And we know through the engineering process, we can either represent images through pixels and JPEG and Fourier and now neural network features, but no one of these is the best way to represent images in all contexts. Also in the brain, we ask this question is how is the brain representing these images? So this is an open scientific problem that biology and evolution has solved. So how do we measure the neural representation? I'm just going to go through this rather quickly. So for the neural representation, we are using grids of electrodes where we place in V4 and IT Cortex, and we get on the order of a few hundred neurons or multi-units that we record from. And when we present images to the awake behaving macaque, we then record spikes. We average up those spikes, and we have tested many different ways to do this, and we essentially are taking the best way we've found thus far to do this, to average the spikes in a certain time window. And you can kind of see for each of these images, we get like a spike count, like a number out per image. And then through all the neurons that we measure, we get out these vectors, which are like feature vectors that you might use in machine learning. Again, it's this rapid serial visual presentation, so we're flashing images very quickly. We're measuring the spikes in a finite time window. And all right, so that's how we measure the neural representation. And then for the deep neural networks, what we did actually beginning in December of 2012, after these first ImageNet results, essentially I contacted Alex and Jeff and Ilya and asked them if they would run our images on their deep neural network that they had usually won the ImageNet challenge with. So they have trained up this large deep neural network on ImageNet, and what I asked them to do is to just compute the features layer-wise through their network using our images, and then again produce for me these types of vectors, essentially these features at the top layers of their networks. So that's how we get to essentially these two different types of feature vectors or representations that we're then going to compare against each other, right? So now we have this way to compare the deep neural networks and the neurons in a specific way. So how do we test an effective representation? And so the concept we want to try to get at is that we wanted an effective representation as one that makes the problem simple. And object recognition is difficult because at the pixel level, essentially the primary sensing of images, object recognition is not a simple problem, right? That's why it's hard. Okay, so we're saying the same thing backwards here. But the process of an effective representation is one that transforms this complex problem from the pixels into a simple one. So that's what an effective representation is doing. It is this transformation from a complex problem into a simple one. And we want to measure that can essentially show this. What we've done is we've turned to an idea that's called kernel analysis. And I'm not going to show a single equation for this audience, but for those that are interested, we're essentially using regularized kernel ridge regression with leave one out error as a measurement. And what we're going to show is like essentially the accuracy as a function of complexity. And I'll show some examples of like a specific feature space as it transforms from something that's complicated to something that's more simple. And I'll show you how this measurement then transforms as well. So in this case, we've got some black dots and some white dots. These are two different classes with some kind of wiggly pattern. So this is a relatively discontinuous function. It's not discontinuous, but it's essentially has lots of curvature to it. And if we plot this curve here, which measures the complexity as a function of the precision, what we see is a specific curve for this specific type of problem. But what becomes interesting is if we look at and compare different representations to each other. So the purple line and this blue line are these two different representations. As you can see, as the representation becomes more simple, has less kind of curvature or variation in that space, the curve pushes up into the lower left, which means that you need a simpler or less complex classifier to maintain the same precision. Right, so you've made the problem easier is kind of what we're seeing through this process. And here's just a few more examples. So again, as the problem becomes simpler, essentially now a linear separation can be happening in this last example. You get to very high precision at very low complexities. So what we're going to do now is we're going to use this measure to measure the deep neural network features and the neurons that we recorded from the brain. So first up, the measurements we got from the brain. We have these V4 neurons there at the bottom. So again, I'm plotting this complexity on the x-axis and this precision on the y-axis. we've had essentially these types of results for a number of years now. And what we, as you expected, as you go through this visual hierarchy, you get to simpler representations of the object problem. And here we're pushing essentially the neurons to a very high level of proficiency where we have lots of variation in terms of the backgrounds and the poses and the positions and the scales, making this a very difficult problem. And then when you begin to look at some of the computational models, what you begin to see are, well, you probably don't see much there, and that's because essentially these models are just not even performing. They're essentially at 0. So we're pushing these models way past their limit. And to give you some examples, some context here, so V1 is essentially like a model of what the primary visual cortex is doing. V2 is like a model of the secondary visual area. H max is maybe a precursor in many ways to some of the latest deep neural networks. It's a hierarchical model that uses max pooling. It, at the surface, looks very much like the way we currently do deep learning, but there are certain elements to it that are missing. So there are certain high-level concepts that are correct in this H-max model, but there are certain elements that are missing that essentially were discovered by the field in the last couple of years. And as we can see here, that they were just completely poorly performing. When we try to keep pushing some of these algorithms to their limit, with these H-max-like models, trying to get better types of learning algorithms in there, we began to see and get models that can kind of compete with V4, for example. And this was kind of the state of the art for a number of years. And then I was looking up the date just the other day. So essentially on December 20th of 2012, I tested Alex Krzyzewski's model. And what we then found is this huge jump in performance. And for the first time, this is like really striking to me. So coming from neuroscience and studying these models for many, many years, we'd always been in this state where like we were saying that the brain was doing something that we didn't know how to do computationally. And now all of a sudden, we had these measurements that seem to contradict that kind of fundamental statement. So it's pretty rare in science that you have to go back and change the introductory slides, right? And this is one of those cases where kind of that fundamental tenet of the difference between computation in artificial systems and in the biology seems to be changing here. So to give you some details here, the red curve is Alex Krzyzewski's model. That's the model with Jeff Hinton, the one that kind of is the first breakthrough in the ImageNet challenge here. And the green curve is Matt Zieler and Rob Fergus's model from NYU. So they showed some improvements in that model and then began to essentially match or about surpass the IT neurons that we had measured. So this has been very exciting to us. And if you don't buy all the kernel analysis stuff, I can also show you the linear SVM as well. So if you do a linear SVM analysis, just take a simple classifier to measure performance. Then you see essentially the same type of result here, where the kind of the older models are just kind of very poorly performing, performing at chance more or less. Then some of these pushing H max to the limit is getting into the 35% regime in this case. And then now these are models from Matt Zieler, who I think is talking later, is essentially matching what we're getting from IT Cortex. And also for those people that know some things about the neuroscience here, we're doing essentially corrections to correct for the noise that we have in the neurons and also for the limited sample size in the neurons. So essentially we're correcting and penalizing the models to try to make this a fair game. In fact, some of our tests show that we think that we are over-penalizing in some ways. So in some ways this might be even an underestimate of some of the deep neural network performance. So here I've talked about representation, but you can also ask about, are the deep neural network neurons like the actual biological neurons? So you can play a different game here where you essentially say, are the deep neural network features, do they predict how the neurons actually spike, how they actually respond? And here again, we've seen a huge dramatic improvement. So this is a different type of measure where essentially we're doing like a generalized linear model for these neurons. And we see this huge jump in performance again for using deep neural networks as models of neurons. But I want to point out that there is still this large gap in the remaining variants that should be explained. There's a bit of information here that we're not fully capturing. I think this is kind of interesting, very interesting scientifically, and maybe influential in terms of making these algorithms even better. just getting in terms of some implications, I know I'm probably running over. I don't know. Vivian is being good to me here. Implications in terms of how we think about the brain. So, you know, these deep neural networks may or not be the right answer to the brain, and I want to point out that in science, all models are wrong, but some are useful. And to the extent that these models are helping us to push our ability to model neurons and to match the performance of the brain, these models are incredibly useful. And for the first time, we're actually able to model some of these areas which even just 5 years ago I thought would have been pretty much a waste of time. But now it's a very fruitful area. I think that, you know, these deep neural networks are likely rival right now and will soon surpass human abilities on these rapid visual discrimination tasks. And also I think this is probably the most exciting thing to me is that deep neural networks may surely surpass any human ability in rapid judgment. So in any case where you have people that are looking at large amounts of data over time and build up some expertise and then make rapid decisions, with access to that same types of data, I think that we can essentially create these algorithms that can be as performant as humans and even more performant. And that's kind of what I'm excited to work about in my next efforts as an entrepreneur here. Also, one thing is we're trying to be very open about this. We have the paper we published is in a public journal. You can get that paper. We've also provided all the images so that you can essentially compute these same curves on your own neural network features, or if you have interest in neuroscience, you can also use these neurons as well. And so the neural data is there. So we have single units and multi-units from these recordings. And just to kind of give you some context on this, there are many caveats here. So I don't mean to say that these deep neural networks are the brain or that they're as good as the biology at large. There are many caveats, and here's just a number of them. We have, you know, reason to believe that this is at least a good answer at this point. But at large, we're very excited about this result and seeing the progress that this interaction of the fields has made. So I could take some questions now. No, put it back on that. There's a question.
Thanks. Actually, two questions. The first one is, did you see the need to do any spike sorting in the beginning to pre-process? Why or why not? And secondly, the complexity curve that you showed.
Let me just answer the first question first. Yeah. So we've used essentially the measurements I showed you here were multi-units. We've also done single-unit spike sorting. So we do spike sorting to get those single units. What we find, in fact, and this is probably worth a longer conversation with you if you're very interested, we found that actually the single units were less performant than the multi-units. Mm. And so that's why I'm essentially I'm trying to give the brain a little bit of a leg up here, and there's probably reasons why that might be in terms of noise reduction, and it's also a very interesting kind of finding in itself.
Sure, sure.
So hopefully that answers the question.
Sure, yeah. And then the second one was the complexity measurement between the biological versus the DNN. Could you just, I guess, go over again how you measured the complexity from the biological standpoint vis-a-vis the DNN?
Sure, yeah. So the process is that
Thank you.
I take as input a feature vector for each of the images in question. And that feature vector either comes from a deep neural network. And for example, in the Alex Krasevsky and Matt Zieler's case, they're the two top layers of their networks. So, but in the neurons, in the neural case, we have these grids of electrodes that measure multiple units at once, multiple neurons at once. And we essentially concatenate those into different feature elements. And then for each image, we get measurements that then construct a feature vector for the brain. Okay? So essentially that gets us to the same space where you got like feature vectors on both sides. Right, so now how do we compute the complexity? Well, what we're doing is we're using kernel ridge regression, which is using a Gaussian kernel in this case. And by changing the regularization knob on that regularization process, we essentially are shrinking the eigenmodes of that kernel. And as you shrink the eigenmodes, you get to more and more smooth functions. So you have this ability to go from very, very complex functions that are essentially like delta functions at each of the data points to very smooth things that essentially become linear separating planes. It's like it's just this nice knob to go from very convoluted classification boundaries to very simplistic classification boundaries. And that knob is essentially just the y-axis, sorry, the x-axis. Excuse me. And I can talk about that at length, the details as well. Yeah.
Right now, actually talking like that and glaze over in the middle of it. I know there were a couple of other questions. I had a quick one that's relevant to this, which is, do you feel like it gave you some insight into the future space of IT units, neurons or collections of local circuits?
I think the verdict is still out a little bit on that, and that is not an easy thing, certainly. And so I think I'll just leave that for future work. And, but I think there's great potential here, and especially as you start to decompose this as a feed-forward approximation to the neurons, and then what is all that's remaining. It gives you kind of like a foothold to stand on.
Yeah. So, one other question right here.
The mic.
So you measured the neurons in the visual cortex. Have you done any analysis on neurons in the memory, so memory neurons within the hippocampus? If you're going to apply kernel analysis to a memory neuron, given that Joseph Ledoux at NYU says that emotions amplify the memory, how would you adjust those sort of contractions and expansions of the spikes in your model?
So first off, we don't measure neurons from the hippocampus or maybe a more memory-related area. So I can't really speak to that, the performance of those neurons. I don't know about specific literature that could actually. In terms of, sorry, was the second part of your question was?
Well, maybe if I might generalize the second part of the question, that we know that these representations, well, we know that local computation in the brain is actually fairly dynamic. So extending from memory research into attentional research, you can see that there was
right, exactly. So you essentially suggest that I should put another bullet on the caveats, which is that we need to also include emotion, full state into the recordings. Yeah, I think that's a very good and fruitful area to go in.
I was wondering whether the missing 20% might be attributed
yeah.
between,
Well, so the
cortex and then the memory neurons, as they are amplified by emotion.
it very well could be, and I think that would be a great experiment to figure out how to do. Yeah, good.
Very cool.
Any other questions? Okay.